Close your eyes and imagine witnessing an act of cosmic violence so extreme that it tears apart an object millions of miles across. A star similar to our Sun, wandering too close to a gravitational monster. The black hole doesn't collide with the star. It doesn't need to. Gravity alone is enough. As the star approaches, tidal forces begin pulling it apart. The side facing the black hole experiences stronger gravity than the far side. This difference stretches the star, elongating it like taffy being pulled. The star's spherical shape distorts into an oval, then an elongated strand of hot plasma. The stellar material doesn't fall directly into the black hole. Instead, it spirals around it, forming an accretion disk, a vast swirling vortex of superheated gas. Friction within this disk heats the material to millions of degrees. It glows brilliantly across the electromagnetic spectrum, from radio waves to X-rays, releasing more energy in a few weeks than our Sun produces in its entire 10 billion year lifetime. This is a tidal disruption event, and for the first time, the James Webb Space Telescope has captured one in unprecedented detail. Not just the aftermath, not just the fading remnants, but the active process of a star being consumed, its matter torn apart and devoured by a black hole 100 million times more massive than our Sun. The images and data Webb collected reveal details never before seen. The temperature distribution within the accretion disk, the velocity of material spiraling inward, the precise moment when stellar material crosses the event horizon, disappearing forever from our universe. And perhaps most remarkably, evidence of material being ejected from the system at nearly the speed of light, polar jets of plasma launched by the black hole's intense magnetic fields. This observation represents a milestone in astrophysics. Black holes are among the most extreme objects in the universe, regions where gravity is so intense that space and time themselves become warped beyond recognition. They cannot be seen directly because light cannot escape them, but when they feed, when they tear apart and consume matter, they become visible through the radiation emitted by their prey. Scientists have observed tidal disruption events before. Ground-based telescopes and space observatories like Chandra and Swift have detected these cosmic catastrophes, primarily through X-ray emissions. But Webb's infrared vision offers something unprecedented: the ability to see through the dust and gas that often obscures these events, revealing structures and processes that were previously hidden. The particular event Webb captured occurred in a galaxy approximately 250 million light-years from Earth. This means the light we're seeing left that galaxy 250 million years ago, during the late Triassic period on Earth, when dinosaurs were just beginning their reign. The star that died did so long before humans existed, but its final moments have only now reached our telescopes, arriving as ancient light, carrying information across 250 million years of cosmic history. Understanding how black holes consume matter is crucial to understanding galaxy evolution. Supermassive black holes exist at the centers of most large galaxies, including our Milky Way. These monsters contain millions or billions of times the Sun's mass, concentrated into regions smaller than our solar system. They profoundly influence their host galaxies through their gravitational effects and through the energy released when they feed. When a black hole actively consumes material, it becomes what astronomers call an active galactic nucleus, or AGN. The energy released can outshine the entire galaxy, radiating more power than hundreds of billions of stars combined. This energy heats surrounding gas, preventing it from collapsing into new stars. It drives galactic winds that blow gas out of the galaxy entirely. It shapes the galaxy's structure and evolution in ways we're still working to understand. But supermassive black holes don't feed continuously. Most of the time, they're quiescent, sitting quietly at galactic centers with nothing falling into them. The regions immediately around them are cleared of gas and stars, scoured clean by previous feeding episodes. They're like cosmic predators that have eaten all the prey in their immediate vicinity and now wait, patient and invisible, for something to wander too close. Tidal disruption events represent those rare moments when a star's orbit brings it within the black hole's reach. Perhaps the star was gravitationally scattered by a close encounter with another star. Perhaps the galaxy underwent a merger that disrupted stellar orbits. Whatever the cause, the star strayed too close, crossed an invisible boundary called the tidal radius, and was doomed. What happens next unfolds over timescales ranging from hours to months. The initial tidal disruption, the actual tearing apart of the star, occurs rapidly, perhaps in a matter of hours, as the star makes its closest approach. But the subsequent accretion, the spiraling inward and consumption of stellar material, continues for weeks or months, gradually fading as the available material is exhausted or dispersed. Webb's observations captured this process at multiple stages. Initial images showed the bright accretion disk, a flattened structure of superheated plasma orbiting the black hole at significant fractions of light speed. Spectroscopic analysis revealed the composition of this material, confirming it was stellar atmosphere, rich in hydrogen and helium, with traces of heavier elements. Follow-up observations weeks later showed the disk had evolved. Some material had fallen into the black hole. Other material had been flung outward by the tremendous forces at play. The overall luminosity had decreased as the feeding rate declined. This temporal evolution provides insights into how quickly black holes process material, how efficiently they convert matter into energy, and how accretion disk dynamics change over time. But perhaps the most exciting aspect of Webb's observations was the detection of relativistic jets. Not all black hole feeding events produce these jets, and scientists don't fully understand what conditions are required. But when jets do form, they represent some of the most energetic phenomena in the universe. These jets consist of plasma accelerated to nearly the speed of light, streaming away from the black hole's poles in two narrow beams. They extend for thousands of light years, sometimes far beyond the host galaxy, carrying enormous amounts of energy into intergalactic space. The mechanism that creates them involves the black hole's rotation and magnetic fields threading through the accretion disk, but the details remain debated. Webb's infrared sensitivity allowed it to detect these jets by observing the shock waves they create as they plow through surrounding gas. The jets heat this gas, causing it to emit infrared radiation that Webb can detect. By mapping the distribution of this heated gas, astronomers can trace the jet's structure and measure their energy output. The implications of this observation extend beyond this single event. By studying how black holes consume stars, we learn about black hole physics, accretion disk dynamics, jet formation mechanisms, and the role supermassive black holes play in galaxy evolution. Each tidal disruption event is a natural laboratory, an experiment we cannot recreate artificially, but can observe and measure in exquisite detail. As we explore this cosmic feast in the following chapters, we'll examine the physics of black holes, the process of tidal disruption, the formation and evolution of accretion disks, the nature of relativistic jets, and what this particular observation tells us about the universe's most extreme objects. We'll trace the journey of stellar material from the moment it's torn from its parent star to the moment it vanishes beyond the event horizon or is ejected into space at near light speeds. This is a story of gravity, energy, and matter pushed to their absolute limits. A story written in the light from an event that occurred 250 million years ago, preserved across the vastness of space and decoded by humanity's most advanced telescope. The story of a star's final moments and the black hole that consumed it. To understand what Webb observed, we must first understand what black holes are and how they warp the fabric of spacetime itself. Black holes are regions where gravity has become so intense that it overcomes all other forces. They form when a massive object collapses to a sufficiently small size, compressing matter to such extreme densities that nothing, not even light traveling at 186,000 miles per second, can escape their gravitational pull. The concept emerged from Einstein's general theory of relativity, published in 1915. Einstein showed that gravity isn't a force, in the Newtonian sense, but rather a consequence of massive objects warping the geometry of spacetime. A planet orbits a star not because the star pulls on it, but because the star's mass curves spacetime, and the planet follows the straightest possible path through that curved spacetime. In most cases, this curvature is gentle. Earth's mass creates a shallow depression in spacetime. The Sun's mass creates a deeper one. But if you compress enough mass into a small enough volume, the curvature becomes extreme. Spacetime warps so severely that it curves back on itself, creating a point of no return called the event horizon. The event horizon is not a physical surface. It's a boundary in spacetime beyond which escape becomes impossible. Once anything, matter or light, crosses this boundary, it inevitably falls toward the black hole's center. No force in the universe can prevent this. The curvature of spacetime itself mandates inward motion. At the very center of a black hole lies the singularity, a point of infinite density and infinite spacetime curvature. Here, Einstein's equations break down. General relativity cannot describe what happens at a singularity. We need a theory of quantum gravity, which we don't yet have, to truly understand this region. But the singularity is hidden behind the event horizon, invisible to outside observers. This is called cosmic censorship, the idea that nature hides singularities behind event horizons, preventing us from observing regions where our physical theories fail. Black holes come in different sizes. Stellar mass black holes form from the collapse of massive stars and typically contain 5 to 100 times the Sun's mass. Their event horizons have radii of perhaps 15 to 300 kilometers, smaller than most cities. Supermassive black holes, like the one Webb observed consuming a star, contain millions to billions of solar masses. Their event horizons are correspondingly larger, ranging from several million to several billion kilometers across. The supermassive black hole at the center of our Milky Way galaxy, Sagittarius A, pronounced A star, contains about 4 million solar masses and has an event horizon roughly 12 million kilometers in radius, about 17 times the Sun's radius. The black hole Webb observed in this tidal disruption event is estimated to contain about 100 million solar masses, based on the dynamics of the disrupted stellar material and the luminosity of the accretion disk. Its event horizon would be roughly 300 million kilometers across, twice the distance from Earth to the Sun. How do such massive black holes form? We don't fully know. Stellar mass black holes form from individual massive stars, but you can't create a supermassive black hole by simply adding stellar mass black holes together. The process would take too long, far longer than the current age of the universe. Current theories suggest supermassive black holes formed early in cosmic history, perhaps from the collapse of massive gas clouds or the cores of the first galaxies. Once a seed black hole of perhaps 1,000 or million solar masses existed, it could grow through accretion of gas and mergers with other black holes. Over billions of years, this growth could produce the supermassive monsters we observe today. Interestingly, nearly every large galaxy contains a supermassive black hole at its center. The mass of the black hole correlates with properties of the galaxy, particularly the mass of its central bulge. This suggests a deep connection between galaxy evolution and black hole growth, a relationship we're still working to understand. Black holes are characterized by only 3 properties: mass, electric charge, and angular momentum, or spin. Everything else about the matter that formed the black hole, its composition, structure, history, is lost. This is called the no-hair theorem, stating that black holes have no distinguishing features or hair beyond these 3 properties. In practice, astrophysical black holes are electrically neutral because any charge would quickly be neutralized by attracting opposite charges. So we really only care about 2 properties: mass and spin. Spin is crucial for several reasons. A spinning black hole drags space-time around with it. creating a region called the ergosphere, where nothing can remain stationary relative to distant observers. Everything must move in the direction of the black hole's rotation. This frame-dragging effect can extract energy from the black hole's rotation, a process called the Penrose process. Spin also affects jet formation. The most powerful jets appear to come from rapidly spinning black holes. The rotation somehow helps magnetic fields extract energy from infalling matter and channel it into narrow beams. We cannot see black holes directly, but we can observe their effects on surrounding matter and light. When matter falls toward a black hole, it heats up through friction and compression, emitting radiation across the electromagnetic spectrum. This radiation allows us to infer the black hole's presence and measure its properties. Gravitational lensing provides another detection method. A black hole's gravity bends light from background objects, distorting their appearance. By observing these distortions, we can map the black hole's gravitational field and estimate its mass. Most dramatically, we can now image the immediate environment of supermassive black holes using radio telescope arrays like the Event Horizon Telescope. In 2019, this collaboration produced the first image of a black hole's event horizon, showing the supermassive black hole at the center of galaxy M87. The image revealed a dark central region, the black hole's shadow, surrounded by a bright ring of emission from the accretion disk. In 2022, the Event Horizon Telescope imaged Sagittarius A, the supermassive black hole at the center of our own galaxy, confirming its properties and appearance match theoretical predictions. These images represent a triumph of observational astronomy and theoretical physics. They confirm that black holes exist, that they have event horizons, and that they match the predictions of general relativity. The theory Einstein formulated over a century ago, working with only pencil and paper, accurately describes these extreme objects. But observing black holes feeding, watching them actively consume matter in real time, provides different insights. It reveals the dynamics of accretion, the behavior of matter under extreme conditions, and the processes that make black holes among the most luminous objects in the universe, despite being fundamentally dark. This is what Webb observed. Not the black hole itself, which remains invisible, but the brilliant display of energy released as a star died, torn apart by gravity and consumed piece by piece. The destruction of a star by a black hole begins with tidal forces, the same phenomenon that creates Earth's ocean tides, but amplified to catastrophic extremes. Tidal forces arise from gravity's inverse square law. Gravitational attraction decreases with the square of distance. This means an object's near side experiences stronger gravity than its far side when close to a massive body. For small objects or large distances, this difference is negligible. But for large objects or close approaches, it becomes significant. The moon's gravity creates Earth's tides by pulling slightly harder on the ocean nearest the moon than on Earth's center, and pulling Earth's center slightly harder than the ocean on the far side. This differential force stretches Earth's oceans, creating bulges on both sides that we experience as high tides. For a star approaching a black hole, the same principle applies but with devastating consequences. The star might be 1,000,000 kilometers in diameter. The black hole's gravity might be millions or billions of times stronger than the sun's. As the star approaches, the gravitational difference between its near and far sides becomes enormous. There's a specific distance, called the tidal disruption radius, or Roche limit, where tidal forces exceed the star's self-gravity. Inside this radius, the star cannot hold itself together. It's torn apart by the gravitational gradient. The tidal disruption radius depends on both the black hole's mass and the star's mass and size. For a sun-like star and a black hole of 100 million solar masses, the tidal disruption radius is roughly 100 million kilometers, about 2/3 the distance from Earth to the Sun. Interestingly, this radius lies outside the event horizon for supermassive black holes. A stellar mass black hole would swallow a star whole before tidal forces could disrupt it. But supermassive black holes have event horizons smaller relative to their tidal disruption radii. stars get torn apart before crossing the event horizon, creating the brilliant accretion disk Webb observed. For extremely massive black holes, billions of solar masses, the tidal disruption radius falls inside the event horizon. Such black holes swallow stars whole without disrupting them, producing no observable signal. This is why tidal disruption events are only observed around moderately massive, supermassive black holes, typically 100,000 to 100 million solar masses. The disruption process unfolds rapidly. As the star approaches closest approach, called pericenter, tidal forces stretch it. Stellar material on the side nearest the black hole is pulled away from the star's center. Material on the far side is left behind as the center accelerates forward. Within hours, the spherical star transforms into a long stream of gas. This stream orbits the black hole in a highly elliptical orbit. Part of the stream, the material that was on the near side, has lost orbital energy to tidal forces and falls back toward the black hole quickly. The other part, the material from the far side, gains energy and is flung outward on a wider orbit. This creates a complex situation. Half the stellar mass is on an inward trajectory, spiraling toward the black hole. The other half is on an outward trajectory, potentially escaping the system entirely. The fate of the star's remains depends on this distribution. The material falling inward doesn't plunge directly into the black hole. It has angular momentum, rotational motion, that must be shed before it can fall in. This angular momentum forces the material to orbit, forming an accretion disk. But the infalling material is still streaming inward, colliding with itself as different portions of the stream intersect. These collisions dissipate kinetic energy as heat, raising temperatures to millions of degrees. The gas begins emitting X-rays and ultraviolet light. Over days and weeks, the stream material settles into a more organized accretion disk structure. This disk is fed by the continuing infall of disrupted stellar material. As long as this material keeps arriving, the disk remains bright and active, radiating enormous energy. The accretion disk around an actively feeding supermassive black hole is one of the most extreme environments in the universe. Material orbits at significant fractions of light speed. Temperatures reach tens of millions of degrees in the inner regions. Magnetic fields, generated by the moving charged particles, thread through the disk and can become dynamically important, affecting the disk's structure and evolution. Friction within the disk causes material to slowly spiral inward. As it does, it heats up further, releasing gravitational potential energy. This energy is radiated away, making the accretion disk shine. The efficiency of this process is remarkable. In a typical accretion disk around a supermassive black hole, perhaps 10% of the infalling material's rest mass energy is converted to radiation. Compare this to nuclear fusion in stars, which converts less than 1% of rest mass to energy. Black hole accretion is the most efficient energy conversion process in the universe, aside from matter-antimatter annihilation. This efficiency explains why feeding black holes can outshine entire galaxies. A black hole consuming just one solar mass of material per year, a modest feeding rate, can radiate 10 billion times the sun's luminosity. If the disrupted star contains one solar mass and half of it falls into the black hole, the energy released over the weeks or months of accretion can equal the sun's total energy output over billions of years. Webb's observations captured this process in infrared wavelengths. While the innermost regions of the accretion disk are hottest and emit primarily X-rays and UV light, the outer regions are cooler and emit infrared. Additionally, dust in the surrounding galaxy absorbs some of the UV and X-ray emission and re-radiates it as infrared, which Webb is optimized to detect. The infrared observations reveal structures invisible to X-ray telescopes. Webb can see through dust that would obscure optical and X-ray observations. It can map the distribution of cooler material in the outer accretion disk and surrounding environment. It can detect dust heated by the accretion disk's radiation. even dust located far from the black hole. Spectroscopic observations with Webb's instruments reveal the velocity distribution of material in the accretion disk. By measuring Doppler shifts in spectral lines, astronomers can determine how fast material is moving and in what direction. This allows them to map the disk's rotation, confirm that material is indeed orbiting the black hole at the speeds predicted by general relativity, and measure the black hole's mass independently. One of the most important results from Webb's observations was measuring the disk's temperature distribution. Theory predicts how temperature should vary with distance from the black hole. Observations can test these predictions. Any deviations suggest processes not included in standard models, perhaps additional heating mechanisms or unexpected cooling processes. The outer parts of the accretion disk, visible to Webb, have temperatures around a few thousand degrees Kelvin. This is hot enough to emit significant infrared radiation, but cool enough that the material remains partially gaseous rather than fully ionized. In these regions, chemistry can still occur. Molecules might form and be destroyed. Dust grains might condense from the gas or be evaporated by the intense radiation field. Webb detected emission from specific molecules and dust species, providing clues about the chemical composition of the disrupted star's outer layers. This composition tells us what type of star was destroyed. A hydrogen-rich atmosphere suggests a main sequence star, similar to our Sun. The presence of heavier elements indicates stellar evolution, perhaps a more evolved star in its red giant phase. The dynamics of the stellar disruption also provide information. By measuring how quickly the brightness increased and how long it took to reach peak luminosity, astronomers can infer the star's orbit and its closest approach distance to the black hole. A star on a deeply plunging orbit gets closer to the black hole, experiences stronger tidal forces, and produces a brighter, faster rising light curve than a star on a more distant orbit. Webb's continuous monitoring over several weeks captured the evolution of the event from peak brightness through its decline. This temporal information is crucial for testing theoretical models. Simulations predict how accretion disks should evolve, how quickly material should be consumed or dispersed, and how the luminosity should change over time. Observations test these predictions. In this particular event, the light curve showed a characteristic shape: rapid rise to peak brightness over about a week, followed by a slower decline over several months. This pattern matches theoretical expectations for tidal disruption events, confirming that Webb indeed observed a star being destroyed and consumed. But there were surprises too. Small fluctuations in the light curve, variations on timescales of days, suggest instabilities in the accretion disk. Theoretical models predict such instabilities, but haven't detailed their exact behavior. Webb's data will help refine these models, improving our understanding of accretion physics. The accretion disk that forms from a tidally disrupted star is a complex, dynamic structure governed by gravity, pressure, magnetic fields, and radiation. Understanding its behavior requires combining general relativity, magnetohydrodynamics, and radiation transport, some of the most challenging areas of theoretical physics. At its most basic, an accretion disk is a rotating disk of gas orbiting a central mass. The material wants to fall inward due to gravity, but its angular momentum keeps it in orbit. For material to actually fall into the black hole, it must somehow lose angular momentum, transferring it outward through the disk. This angular momentum transport occurs primarily through viscosity, a kind of friction within the gas. But the origin of this viscosity puzzled astronomers for decades. Simple molecular viscosity, atoms colliding with each other, is far too weak to explain observed accretion rates. The solution involves turbulence driven by magnetic fields, a process called the magneto-rotational instability, or MRI. Even weak magnetic fields threading through the disk can become unstable, creating turbulent motions that effectively transport angular momentum outward while allowing material to drift inward. Computer simulations of accretion disks including magnetic fields, show vigorous turbulence. Material doesn't smoothly spiral inward, but instead follows chaotic paths, with some regions moving inward, others outward, and the overall trend being gradual infall. This turbulence also generates heat through friction, which radiates away, making the disk luminous. The disk's temperature varies with distance from the black hole. Near the black hole, gravitational forces are stronger, orbital velocities are higher, and friction generates more heat. Temperatures can reach hundreds of millions of degrees. Material is fully ionized into a plasma of free electrons and nuclei. Further out, temperatures decrease. At the distances Webb observes, temperatures might be thousands to tens of thousands of degrees. Here, atoms can exist, and spectral lines from hydrogen, helium, and heavier elements become visible. These lines provide the spectroscopic information Webb uses to measure velocities and composition. The disk's thickness also varies. In the hottest inner regions, high pressure inflates the disk, making it geometrically thick but still optically thin, meaning light can escape from the interior. This hot, thick structure is sometimes called an ion torus, or advection-dominated accretion flow. In cooler outer regions, the disk is geometrically thin, but optically thick. It resembles a flattened pancake, with most emission coming from the surface. This is the classic thin disk model that describes many accretion systems. Webb's observations primarily probe the outer disk regions where infrared emission originates, but by combining Webb's data with X-ray observations from telescopes like Chandra or NuSTAR, astronomers can reconstruct the full disk structure from inner to outer regions, from X-ray to infrared wavelengths. One of the most interesting features Webb detected was asymmetry in the disk. Instead of being perfectly axisymmetric, showing the same structure at all angles around the black hole, the disk showed bright regions and dim regions. This asymmetry suggests several possibilities. First, the disk might be warped or tilted relative to the black hole's spin axis. Tidal disruption events inject material with angular momentum that might not align with the black hole's equatorial plane. The resulting disk could be tilted, twisted, or precessing like a wobbling plate. Second, instabilities in the disk could create local enhancements in density and temperature. These overdense regions would emit more brightly, appearing as bright spots in the disk. As the disk rotates, these spots would move, creating variability in the observed light. Third, the jets observed in this event might affect the disk structure. Where jets extract energy and angular momentum from the disk, the local conditions could differ from surrounding regions, creating brightness variations. Webb's ability to resolve spatial structure in the accretion disk is limited by the distance to the event and the telescope's angular resolution. At 250 million light-years, even Webb cannot resolve individual features within the disk. But by observing how brightness varies with time and wavelength, astronomers can infer spatial structure. For example, if a bright spot in the disk orbits the black hole, it would create periodic variations in brightness as it comes into and out of view. The period of these variations reveals the orbital period, which depends on the distance from the black hole. By measuring this period, astronomers can locate the bright spot within the disk. Similarly, if the disk is tilted relative to our line of sight, one side approaches us while the other recedes. Material approaching us shows blue-shifted spectral lines due to the Doppler effect. Receding material shows red-shifted lines. By mapping these Doppler shifts, astronomers can reconstruct the disk's orientation and rotation pattern. Webb's spectrographs detected both blue-shifted and red-shifted emission, confirming the disk's rotation and allowing measurement of orbital velocities. The velocities match predictions for material orbiting a 100 million solar mass black hole at the observed distances, providing independent confirmation of the black hole's mass. The composition revealed by spectroscopy also tells us about the disrupted star. Emission lines from hydrogen, helium, carbon, nitrogen, and oxygen appear in the spectra. The relative strengths of these lines indicate the star's chemical composition, which in turn reveals its mass, age, and evolutionary state. The detected composition suggests the disrupted star was similar to our Sun, a main sequence star fusing hydrogen into helium in its core. It hadn't yet evolved to red giant status, which would show different elemental abundances. This tells us the star was relatively young, perhaps a few billion years old or less. One surprising finding was the detection of heavier elements like iron in the disk emission. These elements were presumably in the star's core, created by nuclear fusion over its lifetime. Their presence in the disk suggests tidal forces disrupted the entire star, not just its outer layers. The core material was torn out and mixed with the atmosphere, creating a chemically inhomogeneous disk. This has implications for understanding tidal disruption physics. Complete disruption requires the star to pass very close to the black hole, within the tidal radius. Partial disruption, where only the outer layers are stripped away, occurs at larger distances. The detection of core material indicates this was a complete disruption, the star passing deep within the tidal radius. The energy release from this event can be calculated. A Sun-like star contains roughly 2 × 10 to the power of 30 kilograms of mass. If half of this falls into the black hole, and 10% of the rest mass energy is converted to radiation, the total energy release is about 10 to the power of 47 joules. That's equivalent to the Sun's total energy output over 200 million years, released in just a few months. This energy heats the accretion disk and surrounding gas, ionizes atoms, accelerates particles, and powers the jets. It represents one of the most energetic events that can occur in a galaxy, aside from a supernova or gamma-ray burst. Webb's observations of this energy release provide insights into black hole feeding efficiency, disk physics, and the processes that make active galactic nuclei among the most luminous objects in the universe. Every tidal disruption event we observe refines our models and deepens our understanding of these extreme phenomena. Perhaps the most dramatic feature Webb observed in this tidal disruption event was the presence of relativistic jets. Narrow beams of plasma accelerated to nearly the speed of light, streaming away from the black hole's poles. Not all tidal disruption events produce jets. In fact, most don't. Out of hundreds of observed events, only a handful show clear jet signatures. This suggests specific conditions are required for jet formation, conditions we don't fully understand. The jets observed in this event extend for at least several thousand light years from the black hole, though their full extent likely reaches much further. They carry enormous amounts of energy and momentum away from the black hole, depositing it into the intergalactic medium. How do jets form? The basic picture involves the black hole's rotation and magnetic fields threading through the accretion disk. As the disk rotates, it drags magnetic field lines around, twisting them. This twisting creates a torsion in the magnetic field, storing energy like winding up a spring. Near the black hole's poles, where the accretion disk is thin or absent, these twisted magnetic field lines can escape vertically. Charged particles, primarily electrons and positrons, become trapped on these field lines and are accelerated to relativistic speeds. The acceleration mechanism is still debated. One possibility is magnetic reconnection, where field lines break and reconnect, releasing stored magnetic energy. Another is continuous acceleration along the field lines as they unwind, like beads sliding down a spinning wire. Whatever the mechanism, the result is 2 jets of plasma shooting out from the black hole's poles at velocities, approaching light speed. These jets are narrow, typically only a few degrees wide, and highly collimated, meaning they don't spread out much as they propagate. The jets are not continuous streams, but rather consist of discrete blobs or knots of plasma ejected episodically. These blobs can be seen moving along the jet in high-resolution radio images, their apparent motions sometimes exceeding the speed of light due to projection effects. The blobs are actually moving at, say, 99% light speed. But because they're also moving toward us, light emitted from later positions catches up with light from earlier positions, making the blobs appear to move faster than light from our perspective. Webb detected these jets not directly, but through their interaction with surrounding gas. As the jets plow through the intergalactic medium, they create shock waves. These shocks heat the gas to thousands of degrees, causing it to emit infrared radiation that Webb can detect. By mapping this infrared emission, astronomers traced the jets' paths and measured their energy output. The jets carry away roughly 10% of the energy released by the accretion disk, a significant fraction. This energy deposition affects the surrounding environment, heating gas and potentially preventing it from collapsing to form new stars. The presence of jets in this event raises questions about what made it special. Why did this tidal disruption produce jets when most don't? One possibility involves the black hole's spin. Rapidly spinning black holes might be more likely to produce jets because their rotation more efficiently powers the magnetic field twisting process. If this black hole spins at close to its maximum rate, where the event horizon rotates at nearly light speed, it could explain the jets. Another possibility involves the accretion rate. Jets might only form when the accretion rate falls within a specific range, not too high and not too low. Too high, and the accretion disk becomes bloated and obscures the polar regions. Too low, and there's insufficient material to power the jets. This event might have had just the right accretion rate. A third possibility is magnetic field strength. The disrupted star's core might have contained stronger magnetic fields than typical, which were then transferred to the accretion disk. These stronger fields could more easily launch jets. We don't know which, if any, of these explanations is correct. All three mechanisms might play roles. Disentangling their relative importance requires observing many tidal disruption events and looking for patterns. Webb's contribution is providing detailed observations of jet-powered events, revealing structures and properties invisible to other telescopes. The infrared emission traces cooler gas around the jets, complementing radio and X-ray observations that show the jets themselves. One of the most interesting findings was a symmetry in the jet emission. The two jets, though presumably launched symmetrically from opposite poles, appear different in Webb's images. One jet is brighter and more extended than the other. This asymmetry likely results from relativistic beaming. Jets moving toward us appear brighter because their emission is Doppler boosted and concentrated forward due to relativistic effects. Jets moving away appear dimmer for the opposite reason. The brightness difference tells us the jet's orientation relative to our line of sight. In this case, the brighter jet is approaching us at a slight angle, perhaps 30 degrees from our. When astronomers analyze light from cosmic events, they're doing far more than simply observing brightness. They're decomposing that light into its constituent wavelengths, creating spectra that reveal the physical conditions, chemical composition, and dynamics of the emitting material. Webb's spectrographs capture detailed spectra of this tidal disruption event across infrared wavelengths, revealing information invisible to our eyes, but crucial for understanding what occurred. The spectrum shows emission lines from hydrogen, the most abundant element in stars. These lines appear at specific wavelengths corresponding to electron transitions in hydrogen atoms, but they're not at their rest wavelengths. Some are blue shifted, meaning the emitting material is moving toward us. Others are red shifted, moving away. This Doppler shifting reveals the accretion disk's rotation. Material on one side orbits toward us, blue shifting its light. Material on the other side orbits away, red shifting its light. By measuring these shifts, astronomers calculate orbital velocities reaching thousands of kilometers per second, significant fractions of light speed. The line widths also carry information. Broader lines indicate more velocity dispersion, material moving at different speeds along our line of sight. This happens in turbulent regions where gas moves chaotically, or where we're viewing material with a range of velocities. The spectrum also reveals temperature through the relative strengths of different ionization states. Hydrogen can be neutral, singly ionized, or fully ionized depending on temperature. Helium shows similar progression. By measuring which ionization states dominate, astronomers infer temperatures. For this event, the infrared spectrum indicates temperatures ranging from a few thousand degrees in the coolest regions to hundreds of thousands of degrees in hotter areas. This temperature gradient maps the disk structure, with outer regions cooler and inner regions progressively hotter. Chemical composition comes from identifying spectral lines of different elements. Besides hydrogen and helium, Webb detected lines from carbon, nitrogen, oxygen, and heavier elements. The relative abundances of these elements tell us about the disrupted star's composition and evolutionary state. The presence of carbon and oxygen in specific ratios suggests the star had undergone nuclear fusion in its core, creating these elements over billions of years. The detection of nitrogen indicates CNO cycle processing, the fusion pathway operating in stars like our Sun. More exotic elements like neon, magnesium, and silicon appear as well, though more weakly. These formed deeper in the star's core through more advanced fusion stages. Their presence confirms the tidal disruption was total, tearing apart the star completely and mixing core and envelope material. Dust features also appear in the infrared spectrum. Silicate dust, composed of silicon and oxygen, creates broad absorption features at specific wavelengths. Carbon-based dust creates different features. By identifying these signatures, astronomers determine what types of dust exist in the environment. The dust might have pre-existed in the galaxy, now illuminated by the tidal disruption's radiation, or it might have formed from the event itself, stellar material cooling and condensing into tiny grains. Distinguishing these possibilities requires careful analysis and comparison to models. Time-resolved spectroscopy, observing how the spectrum changes over weeks and months, reveals the event's evolution. Early spectra show higher temperatures and faster velocities as fresh stellar material rains down onto the accretion disk. Later, spectra show cooling and slower accretion rates as the supply of disrupted material diminishes. This temporal evolution can be compared to computer simulations that predict how tidal disruptions should evolve. The agreement between predictions and observations tests our theoretical understanding and reveals whether our models capture the essential physics. One surprising spectroscopic finding was the detection of high-velocity outflows in addition to the jets. These outflows, moving at a few percent of light speed, appear to be material blown away from the accretion disk by radiation pressure or magnetic forces. Such outflows are predicted theoretically, but hadn't been clearly detected in many previous tidal disruption events. Webb's sensitivity and spectral resolution made them visible, adding another piece to the puzzle of how black holes interact with their surroundings. The outflows carry mass and energy away from the system, reducing the amount of material that ultimately falls into the black hole. This affects the black hole's growth rate and the overall energy budget of the event. By measuring the outflow velocity and the amount of material involved, astronomers can calculate how much energy is carried away. This mechanical energy, combined with the radiated electromagnetic energy and the jet energy, accounts for the total energy released during the disruption. Balancing this energy budget is crucial for understanding accretion physics. Energy comes from gravitational potential energy as matter falls toward the black hole. That energy must go somewhere: radiation, jets, outflows, or into the black hole itself. By accounting for all channels, we verify energy, conservation, and test whether our models are complete. Webb's spectroscopic observations provide much of the information needed for this accounting, revealing outflows and disk dynamics that would be missed with imaging alone. The spectrum also contains information about the environment beyond the immediate accretion disk. Absorption lines from intervening gas between us and the event reveal what lies along our line of sight. This gas might be in the host galaxy or in intergalactic space. For this event, the absorption spectrum shows features consistent with the host galaxy's interstellar medium. Gas clouds containing hydrogen, carbon, and other elements absorb specific wavelengths, creating dark lines in the spectrum. The strength and width of these absorption lines reveal the amount and velocity distribution of intervening material. Interestingly, some absorption features are blue-shifted relative to the host galaxy, indicating they come from gas moving toward us. This might be material previously ejected from the galactic center, now in the line of sight between us and the tidal disruption event. All this information, extracted from careful analysis of how light intensity varies with wavelength, paints a detailed picture of the event's physics, far richer than simple imaging could provide. Spectroscopy transforms pretty pictures into quantitative science, converting photons into measurements of mass, velocity, temperature, composition, and energy. It's one of astronomy's most powerful tools, and Webb's infrared spectrographs are among the best ever built. This tidal disruption event, remarkable as it is, represents just one instance of a broader class of phenomena occurring throughout the universe. Billions of galaxies contain billions of supermassive black holes. Trillions of stars orbit those black holes. Occasionally, inevitably, orbits intersect and stars are destroyed. The rate of tidal disruptions is estimated at roughly 1 per 10,000 years per galaxy. In a universe containing perhaps 2 trillion galaxies in the observable volume, this means roughly 200 million tidal disruptions occur every year somewhere in the cosmos. Most go unobserved. They're too distant, too obscured by dust, or pointing the wrong direction if they produce jets. But thousands are potentially detectable with current instruments if we look at the right place at the right time. As survey capabilities improve, the detection rate is increasing. What was once a rare exotic phenomenon is becoming a regular occurrence in astronomical catalogues. This transition from rare to common is scientifically valuable, enabling statistical studies that reveal patterns individual events cannot show. The cosmic rate of tidal disruptions also has implications for black hole growth. If each event feeds 1 million solar masses of stellar material to a black hole, and events occur every 10,000 years, that's 100 solar masses per million years. Over a galaxy's 10 billion year lifetime, that's 1 million solar masses from tidal disruptions alone. This is significant, but not dominant compared to gas accretion, which can feed supermassive black holes at rates of solar masses per year during active phases. Still, tidal disruptions contribute to overall black hole growth, particularly during quiescent periods when gas accretion is minimal. The events also contribute to the chemical enrichment of galaxies. Disrupted stars contain heavy elements created through nuclear fusion. Some of this material is ejected from the system in outflows or jets, mixing with the interstellar and intergalactic medium. Over billions of years, countless tidal disruptions have scattered stellar material throughout galaxies and beyond. This material becomes available for future star formation, carrying the chemical legacy of stars that died violently rather than quietly. The jets from tidal disruption events also affect their environments on larger scales. As jets propagate through intergalactic space, they inflate enormous bubbles of hot gas, displacing cooler material and preventing it from collapsing to form stars. In galaxy clusters, these bubbles can be observed as cavities in the X-ray emitting gas, regions where jet energy has pushed aside the hot intra-cluster medium. While most of these cavities result from long-lived active galactic nuclei, some might originate from powerful tidal disruption events. The energy injected by jets can remain in the intergalactic medium for hundreds of millions of years, long after the original event has faded. This represents a form of black hole feedback operating on galactic and cluster scales, shaping the evolution of cosmic structure. Understanding this feedback is crucial for understanding why the universe looks the way it does. Without feedback from black holes and supernovae, theoretical models predict far more stars should have formed than we actually observe. Feedback mechanisms regulate star formation, keeping it at observed levels. Tidal disruption events are one component of this feedback, contributing episodically when stars are disrupted rather than continuously like sustained accretion. Their role in the overall feedback budget is still being quantified, but observations like Webb's help refine the estimates. On even larger scales, the observable universe contains structures and patterns that reflect its evolution over cosmic time. Galaxies cluster together in groups and clusters. These cluster into superclusters. Superclusters connect via filaments forming the cosmic web, surrounding vast voids where few galaxies exist. This large-scale structure emerged from tiny density fluctuations in the early universe, amplified over billions of years by gravity. Dark matter provided most of the gravitational attraction, while ordinary matter fell into the dark matter's gravitational wells. Supermassive black holes formed at the densest points, galaxy centers. They grew along with their host galaxies through a complicated co-evolution process we're still unraveling. Tidal disruptions are one small piece of this cosmic story, markers of black hole growth and galaxy evolution visible across cosmic time. The event Webb observed occurred in a galaxy 250 million light-years away, meaning we see it as it was 250 million years ago. But similar events are occurring at all cosmic distances, from nearby galaxies a few million light-years away, to distant galaxies billions of light-years distant. Observing tidal disruptions at different cosmic distances reveals how the phenomenon has evolved over cosmic time. Were disruption rates higher in the past, when galaxies were more gas-rich and dynamically active? Do the properties of disruptions change as black holes and galaxies age? Answering these questions requires observing events across cosmic time and comparing their properties. Webb's ability to detect infrared emission from distant events makes it ideal for such studies, complementing observations of nearby events by other telescopes. The ultimate context is philosophical rather than purely scientific. We're observers in a universe that existed long before us and will continue long after we're gone. The events we observe, the stars being destroyed, the black holes feeding, all occurred in the distant past and are now finished. We're seeing cosmic history unfold, light from ancient events reaching us now. This gives astronomy a temporal depth unique among sciences. We're not just studying the universe as it is, but as it was, looking back through time across vast distances. Every photon Webb collects is a messenger from the past, carrying information across space and time to our instruments. The star whose death we're observing was destroyed 250 million years ago. Its death cry, encoded in electromagnetic radiation, has been traveling through space ever since, finally reaching us now. In a sense, we're witnesses to cosmic events we could never attend directly, separated by distances and time so vast that physical travel is impossible. But light bridges that gap, connecting us across the cosmos to events that shape the universe we inhabit. This is the privilege and wonder of astronomy, connecting across cosmic scales, understanding phenomena we can never touch, building knowledge of a universe far larger and older than ourselves. As we reach the conclusion of our journey through this cosmic catastrophe, it's worth reflecting on what we've learned and what questions remain. James Webb's observation of a black hole consuming a star represents the culmination of centuries of astronomical progress. From Galileo's first telescopic observations 4 centuries ago to Webb's infrared vision revealing structures billions of light-years away, we've extended human perception across cosmic distances. Each technological advance enables new discoveries. Galileo saw Jupiter's moons and realized Earth wasn't the center of everything. Herschel discovered infrared light and expanded the electromagnetic spectrum we could study. Hubble revealed an expanding universe filled with billions of galaxies. Webb pushes further still, seeing in infrared with unprecedented clarity and sensitivity. The tidal disruption event we've explored throughout this journey showcases Webb's capabilities. The detailed imaging reveals spatial structure in the accretion disk and jets. The spectroscopy measures velocities, temperatures, and composition. The temporal monitoring tracks the event's evolution from outburst to fade-out. But beyond technical capabilities, this observation represents something more profound. humanity's ongoing quest to understand the universe we inhabit. We're curious creatures, driven to ask questions and seek answers. Why does the universe exist? How did it begin? What are its fundamental laws? How will it end? These are ancient questions, pondered by philosophers and theologians throughout human history. Science provides a methodology for addressing them through observation, experimentation, and logical reasoning, rather than revelation or tradition. The scientific answers, while impressive, are always provisional. We build models that match observations, but we recognize those models are approximations, useful but incomplete. General relativity accurately describes black holes and space-time curvature, but we know it's incompatible with quantum mechanics at fundamental levels. This tension between theories drives much current physics research. Somewhere, somehow, a deeper theory must exist that encompasses both general relativity and quantum mechanics, explaining both the large-scale cosmos and the microscopic quantum realm. Observations of black holes eating stars won't directly reveal that deeper theory, but they provide constraints and tests. Any complete theory must reproduce what we observe: matter spiraling into black holes, energy being radiated, jets launching from magnetic fields, threading through accretion disks. Every observation adds another constraint, narrowing the space of possible theories, guiding theorists toward truth through an incremental process of refinement and testing. The star that died in this event is gone, its matter consumed or scattered. From a cosmic perspective, this is insignificant. One star among hundreds of billions in that galaxy, one galaxy among trillions in the universe. Matter rearranging itself according to physical law, nothing more. But from our perspective, it's extraordinary. We detected the event across 250 million light-years of space. We measured its properties. We understood what happened through careful analysis and theoretical modeling. We learned something new about how the universe works. This capacity for understanding, for extracting meaning from photons and mathematics, represents something remarkable about consciousness and intelligence. We're arrangements of matter complex enough to contemplate our own existence and ponder the cosmos that created us. The universe is not trying to hide its secrets. It operates according to consistent laws that we can discover through patient observation and clever experimentation. This comprehensibility is perhaps the greatest mystery of all. Why should the universe be understandable? Why should mathematical equations describe physical reality? These questions venture into philosophy and perhaps have no scientific answers. But the fact remains, the universe is comprehensible, at least partially, and we're comprehending it more completely with each passing generation. The tidal disruption Webb observed adds to that comprehension. Future events will add more. Gradually, piece by piece, we're assembling a complete picture of black hole physics, accretion processes, and galaxy evolution. This work continues. Webb is observing now, collecting data on new events and following up on this one as it fades. Other telescopes across wavelengths and across Earth are doing the same. Theorists are refining models, running simulations, making predictions. The scientific enterprise is collective and cumulative. No single person or observation unlocks all mysteries. Instead, thousands of researchers contribute small pieces, each building on what came before, collectively advancing human knowledge. The observation we've explored in such detail is one contribution among many. Important? Yes. Revealing new insights? Absolutely. But part of a larger tapestry of discovery that extends back centuries and will continue for centuries more, as long as curiosity drives us to ask questions and seek answers. And so, the story continues. Stars continue orbiting black holes across the universe. Some wander too close. Tidal forces tear them apart. Black holes consume them. Jets erupt. Energy floods space. And somewhere, telescopes built by curious beings point toward these events, collecting ancient light, extracting meaning. This is the ongoing dialogue between Humanity and Cosmos, Question and Answer, Observation and Understanding. A dialogue that began when our ancestors first looked up at the night sky and wondered, continuing now with the most sophisticated instruments ever built, and extending into a future we can only imagine. In the quiet darkness of space, 250 million light-years from Earth, a galaxy continues its ancient rotation. At its center, a supermassive black hole sits invisible, patient, eternal. The star it consumed is gone, its matter added to the black hole's mass or scattered across space. The brilliant accretion disk has faded. The jets have weakened and dispersed. Eventually, all evidence of the event will disappear. The heated gas will cool over millions of years. The disturbed orbits will relax. The galaxy will return to its previous state, unchanged except for a black hole incrementally more massive and stellar orbits fractionally rearranged. But somewhere in that galaxy, other stars continue their orbits, unaware that one day, perhaps millions of years from now, their own paths might bring them too close to the central monster. The dance continues, gravity choreographing movements across cosmic scales, occasionally bringing star and black hole together in a fatal embrace. And across the universe, in billions of other galaxies, the same dance plays out. Stars orbit, black holes wait. Occasionally they meet. Energy blazes forth. Then darkness returns. This is the rhythm of the cosmos, patient and inexorable. Stars form from collapsing gas clouds, live out their nuclear lifetimes, and die in various ways. Some explode as supernovae. Others fade quietly as white dwarfs. An unlucky few are torn apart by black holes. Each ending is also a beginning. Supernova remnants enrich space with heavy elements, enabling future star formation. White dwarfs cool over trillions of years, eventually becoming dark stellar corpses. Tidally disrupted stars feed black holes and heat surrounding gas, affecting future galaxy evolution. The universe recycles its matter endlessly, transforming it through various states, but never destroying it, at least not until the far future when proton decay or black hole evaporation might reduce everything to radiation and dispersed particles. But that future is unimaginably distant, trillions or quadrillions of years from now. For the present cosmic epoch, matter remains stable, gathering into structures under gravity's patient pull, igniting into stars, orbiting in galaxies, occasionally encountering black holes in spectacular displays of violence and energy. We observe these displays from our small planet, using instruments that extend our senses across cosmic distances. We decode the messages carried by ancient light, reconstructing events we could never witness directly. This observation, this understanding, is itself remarkable. Conscious beings emerged from stellar ashes, evolved through billions of years of biological evolution, developed technology and science, and now comprehend the deaths of distant stars consumed by gravitational monsters. The universe has become aware of itself through us, at least in this small corner of space and time. We're the cosmos examining itself, matter arranged in such specific ways that it can contemplate its own existence and origins. This self-awareness is temporary and fragile. Civilization could end through various means. Even if it persists, the universe will eventually become inhospitable to complexity and consciousness, fading into heat death over timescales that dwarf the current cosmic age. But for now, for this brief cosmic moment, awareness exists. Questions are asked, observations are made, understanding grows. The black hole that consumed a star doesn't know or care that we observed the event. It continues existing, warping space-time around itself, occasionally consuming matter that ventures too close, operating according to the deterministic laws of general relativity without purpose or intent. But we care. We observed. We understood. And in that understanding, we found meaning, even in a process that's ultimately just matter and energy rearranging themselves according to physical law. Perhaps meaning isn't inherent in cosmic events, but rather something we create through observation and understanding. The tidal disruption has no intrinsic significance, but we give it significance by studying it, learning from it, incorporating it into our growing comprehension of how the universe works. And so we continue observing, continue questioning, continue building our collective understanding of the cosmos. Each observation adds another piece to the puzzle. Each question answered raises new questions. The process has no obvious endpoint, just ongoing discovery and wonder. Sleep now and dream of stars dancing around black holes, of matter spiraling inward releasing energy, of jets streaming across cosmic distances, of photons traveling for hundreds of millions of years to reach our telescopes and reveal ancient secrets. Dream of a universe vast beyond comprehension, filled with structures and processes we're only beginning to understand, where black holes devour stars and space itself expands, carrying galaxies ever further apart. Dream of humanity's quest to understand this universe, building ever more sophisticated instruments, developing ever more refined theories, gradually illuminating the darkness with the light of knowledge. The universe continues its ancient dance, indifferent to our observations, but we observe nonetheless, driven by curiosity and wonder, adding our small contribution to the grand story of cosmic evolution. And somewhere, right now, a star is wandering too close to a black hole. Tidal forces are beginning to stretch it. The fatal dance is starting again. And when the light from that event reaches us, perhaps decades or centuries from now, we or our descendants will observe it, measure it, understand it, and marvel once more at the universe's terrible beauty. Rest now. The cosmos will still be there when you wake, and the dance will continue, patient and eternal, under the patient gaze of whatever consciousness remains to witness it.